So I will talk about a moment-based approach for the analysis of the infinitesimal model, and this is a joint work with Jessica Guérand and Mathieu Hilleret, who are both in Montpellier. I think that Vincent presented already a talk on the infinitesimal model, so you're already familiar with the equation. So this model describes a phenotypically structured population under the effect of selection and sexual reproduction. Here, n corresponds to the density of individuals with trait X at time t, and rho of t is the total population size. So the dynamics of this phenotypic density is governed by a sexual reproduction operator T sigma, that I will describe a little bit later, and also a death term via a function that corresponds to the intrinsic death rate, mg of x, intrinsic death rate of individuals with trait X, and kappa rho, which corresponds to a uniform competition term leading to death rate. And for this function mg of x, we will assume here that it has a local minimum at 0, that it is smooth and its derivative is equal to 0 at 0, and second derivative is positive at 0, equal to 2g. And this g will be called the strength of selection around the point x equal to 0. Which means that it measures somehow how the death rates becomes important around 0. So what is the infinitesimal model? This is a classical model in quantitative genetics, a classical model of reproduction. If the parental traits are given by x1 and x2 in this model, the trait of the offspring would be given by the average of x1 and x2 plus a random variable which follows a Gaussian distribution. And in terms of our equation, the reproduction operator is then written in this form of a double integral term, where we have this terms n of y times n of y prime over rho, which corresponds to the rate with which individuals of trait y and trait y prime meet. And then we have this Gaussian distribution, which corresponds to the distribution around which the offspring is distributed. And the variance of this Gaussian distribution is usually referred to as segregational variance. This model has been justified from allelic models when the trait X is coded by different infinitely many genes with additive small effects. It was suggested by Fischer in 1918, and it was justified rigorously more recently by Barton, Etheridge, and Weber in 2017. So the question is, what is the shape of the solution to such equation, and how does the solution evolve? A very common approximation in quantitative genetics is to assume that the population has a Gaussian distribution. So the population, because the infinitesimal model itself, it only supposes that the distribution of the offspring has a Gaussian distribution. So this is the assumption. And then this is an approximation that the population itself has also a Gaussian distribution, and that the phenotypic density can be approximated by a Gaussian distribution with a constant variance, here sigma squared, but with a mean that can change over time, and also with the population size that can change over time. And these such type of approximations are made for many models with possible spatial or temporal heterogeneity of the environment. And the question then is, then becomes on how to derive the dynamics of rho and mu, so the moments of the phenotypic distribution. And the natural question is, can such an approximation be justified? And if yes, under which assumptions? So let me introduce some change of variables. I'm not going to the details of the change of variables, but I introduce this in such a way such that m second derivative of m at 0 becomes 2. So it's the strength of selection is set equal to 1. And in what follows, I will assume that sigma square root of g over square root of r is small, and I will call it epsilon. So I recall that sigma was the segregational variance, g was the strength of selection, and r was the reproduction rate. So morally, this assumption means that the evolutionary dynamics will be slower than the demographic dynamics. I also make a change of variable in n, and I also renormalize it such that its integral is equal to 1. So I obtain in this way a function q epsilon that is a probability density for all time. Okay, again, I'm not going to the details of how I do this renormalization and reparametrization, but just believe me that this new function then satisfies this equation. So what is the difference with the initial equation is that now the reproduction rate is set equal to 1. The strength of selection is also set equal to 1. And the segregational variance here is set equal to epsilon, which is a small parameter. And we have these terms minus q epsilon and minus integral of mq, which appear in order to that we have a probability density and the population size is conserved. And we have also this epsilon squared in front of dt, which comes from the change of variable in time. And the reason we have made such a change is that we expect that the evolutionary dynamics would be slow. And in order to follow such slow dynamics, we make a change of variable in time to be at this time scale. Okay, and the question is then, what is the asymptotic behavior of q epsilon as epsilon goes to 0? And this question is not new, and actually this equation with this scaling was introduced first by Calvez, Garnier, and Patou, and there are several articles on such scalings and such questions. And they are generally based on an approach where they use a Hopf transformation and a perturbative analysis approach. Here, I will present a new method with a moment-based approach. Okay, so the approach is different. There is also an equivalent formulation of this problem. Again, with the change of variable, I can rewrite the problem in this form where the segregational variance is set equal to 1. But there is an epsilon x in the mortality rate m. So this can somehow be seen as what we say in quantitative genetics as weak selection. And it is also related to some works by Gaël Raoul, who also studies the weak selection regime. But the frameworks are rather different because, for instance, in his article in 2021, he considers the X dependence in the reproduction rate and not in the mortality rate. And there he assumes that the reproduction rate is a perturbation of 1 in the form of 1 plus epsilon r of y with r compactly supported. So here the epsilon is outside of r, and it's a coefficient to say that it is small, while we have epsilon in the variable x in front of the variable x. So these are related, but they're not the same frameworks. Before going to the results, I would like to comment a little bit these operators that are in the source stem separately. First of all, we can consider a model where we only have the death rate, the death term, but not the reproduction term. And we assume that Q naught is a probability density, M and Q naught are both smooth, and that M has a strict unique minimizer in the support of Q naught. Okay, and we will call this X naught. In this case, we can show that there is a unique global solution to this equation, which is a probability density for all times. And as t goes to infinity, Q will converge to a Dirac mass that is concentrated at the point x naught. So what happens is that this equation would concentrate the solution in long time as a Dirac mass at the point x naught. And the point where the solution gets concentrated is well defined. It's in a unique way. And now what would happen if we have only the reproduction rate and not the mortality? So again, we assume that Q naught is a probability density, and it is a smooth. And we will denote by x naught bar to be the initial phenotypic mean of the population, the first moment of Q. In this case, we can also prove that there exists a unique global solution Q to this equation that is also a probability density for all time. And as t goes to infinity, Q now will converge to a Gaussian distribution. And this Gaussian distribution will be centered around x bar naught. And its variance is given by 2 sigma, which is twice the variance, the segregational variance in the reproduction operator. Okay, so we see that if sigma was small, then it means that the solution is still getting concentrated with a variance of order epsilon squared. Okay, I think that I have a notation problem. Okay, so this is not very important. I don't know if I put how I defined gamma. Okay, so it's the square root of the variance. So if it is the square root of the variance, then I have to put the square root of 2 also in front of sigma here. I'm sorry for that. So the variance would be twice the variance of the segregational variance. Okay? And this is something that can be proved following some arguments given by Magal and Raoul in 2015. And it is based on 2 main elements, that gamma 2 sigma is indeed a fixed point of this operator, T sigma. And also there is a contraction property of T sigma in the Wasserstein distance 2. And from these 2 properties, we can obtain such a result. So in summary, both of these operators tend to concentrate the solution when sigma is small. In the first case, the solution gets concentrated at a single point, which is the minimum point of the mortality rate. In the second equation, however, we can have infinitely many options for the steady states. The solution can get concentrated on any point in the space, but this point would depend on the initial condition. Now, what would happen if we have the complete model? So it would be easier to comment this. So I have the complete model with the scaling that I introduced, so a small segregational variance, and I will accelerate time. So I will try to explain this with a figure. So here is we have the mortality rate M. I will assume that its minimum is equal to 0. This is, of course, arbitrary. It's just to get it can be set to any point. Here I will put it to, without loss of generality, I can say that the minimum of M is equal to 0. Then what happens when I have the complete model is that the solution, okay, when we combine the both operators, the solution will get concentrated again. And it will get concentrated as a Gaussian approximation imposed by the reproduction operator. However, now the points where the solution gets concentrated in long time, so the steady states, would be more restricted. And the points that the solution can get concentrated are the points in red, which correspond to the extremum points of M. So the minimum points or the maximum points of M, which are local minimum points, while if we had only the mortality rate, the solution would have concentrated only at this point, where, I don't know if you see my cursor, but if we had only the mortality rate, the solution would have concentrated on the global minimum. But now, with the combination of both, we can have also local minimum points of concentration points. But for the solution, for the steady state to exist as a concentrated Gaussian around these points, the value of these points have to be less than 1. Okay, so this is okay, so the picture is rather different when we combine the both operators. And when we have the dynamics, so this was about the steady state and what happens for the dynamics. Well, for the dynamics, if we start from a point, for instance, around the minimum 0, if we start around 0, then the solution will remain concentrated and it will gradually approach the local minimum 0, and it will follow the minus gradient of M. Sorry. So this is okay, so this is something that, okay, I see the problems of the slides. Okay, so this is something that, again, it was proved in the paper of Patou, and I will show this. The main part of my talk will be concentrated on these properties of the dynamics of Q epsilon when we start with the well-prepared initial data. And at the end, I will present some remarks on the steady states based on work in progress with material error. And maybe some notations to be able to present the results. I will call M epsilon 1 to be the first moment of Q epsilon, and M epsilon Kc to be the central the case of the central moment of Q epsilon. So by this definition, M epsilon 0c is equal to 1 and M epsilon 1c is equal to 0. Okay. Okay, now this is the plan of my talk. I just finished my introduction. Now I will present the dynamics with our results on the dynamics of Q epsilon, and then I will give some main ingredients of the proof, and then I will comment the steady states. So these are my assumptions. I will assume that M is smooth. I will be interested in what happens around one of the local minima that I will consider to be at the point 0. So I assume that the global minimum of M is equal to 0, and it has a local minimum at 0. So we have that M prime of 0 is 0, and M is strictly convex around this minimum point, and that the value of M is less than 1. Okay, so why 1? Yeah, maybe one can wonder why the threshold 1. This should be interpreted as the global minimum of M plus reproduction rate R. Here, the global minimum is 0, and the reproduction rate is 1. So this is why the 1 is here, the threshold. And we have this technical assumption on the second derivative of M that it has at most polynomial growth. And for the initial condition, we assume that it is well prepared in the sense that initially the first moment is close to x0, with x0 in the convexity zone around the point 0, and that for some k naught large enough, the moment of order 2k naught, the central moment, is of order epsilon to the power 2k naught. Note that when we have we are expecting the solution will approach a Gaussian distribution with a variance epsilon squared, and a Gaussian distribution with variance epsilon squared has its k naught order moment of order epsilon 2k naught. So this only means that initially somehow the solution is has somehow a similar shape to the Gaussian distribution with variance order epsilon squared. And also a notation, I will define G epsilon to be a Gaussian distribution, which has its variance equal to epsilon squared, and its mean equal to z bar epsilon, where z bar epsilon solves this ODE. So z bar epsilon dot is given by minus m prime of z bar epsilon, and with the initial condition given by m epsilon 1 of 0. So this is the candidate for the approximation of Q epsilon. So we will show that Q epsilon is close to this Gaussian distribution. And we can see that as epsilon goes to 0, z bar epsilon will converge to some function z bar, which solves the same equation, but with a different initial condition, which is the limit of m epsilon 1 of 0 given by x naught. Okay, so this is our main result. We can prove that Q epsilon and if Q epsilon naught and G epsilon naught are initially closed, then Q epsilon and G epsilon will remain closed for all times in Wasserstein distance 1, W1. And so this is for the approximation of the phenotypic distribution. What can we say on the population size? We can also approximate rho epsilon by some function rho, which is given by r minus m of z bar of t over kappa. And this approximation holds for all t after some small time epsilon to the power beta, with beta between 1 and 2. So in particular, as epsilon goes to 0, and epsilon will converge to a Dirac mass, which is centered at the point z bar of t, and with a weight rho bar of t. Okay, and in order to prove this result, a main ingredient is this second theorem, where we estimate the moments of the phenotypic distribution. And we actually show that the moments of the phenotypic distribution are close to the moments of the Gaussian distribution G epsilon. For instance, we show that m epsilon 1 is close to z bar epsilon, with some error, epsilon 1 minus delta, with delta, where delta can be arbitrarily small. And m epsilon 2c, so the variance can also be approximated by epsilon squared, and that the moment of order 2k naught, we can prove that it is of order epsilon 2k naught. So it has the right order for k naught large enough. I mean, for k naught that we had at the in our assumption. So we had supposed that this was true initially, and what we prove is that it remains true for all times. Okay, so in the next part of my talk, I will try to give some ingredients of the proof of this second theorem. Once we have this theorem, then we can use these approximations to obtain the result on the Wasserstein distance. But today I'm not going to develop that part. I will just show you why we can obtain such estimates on the moments. So I recall the equation that we have on Q epsilon, and to control the moments, the idea is actually rather simple. We will multiply the equation by x, or x minus m epsilon 1 to the power k, and then we will integrate, and we will obtain some equations on the moments. And we will have some computations on these moments in order to obtain our results. So there are some properties that allow us to estimate these, so to simplify or to study these equations on the moments. First of all, there are some algebraic properties of this infinitesimal operator, T epsilon. For instance, it preserves the phenotypic mean, so the first moment. The first moment is preserved, so integral of x times T epsilon Q epsilon is equal to the first moment of Q epsilon. And for the second central moment as well, we have a nice property that is x minus m epsilon 1 squared times T epsilon Q epsilon, etc. The integral of this term is given by epsilon squared over 2 plus m epsilon 2c over 2. And for higher order moments of order 2k, we can also have some algebraic computations, and we can write this integral in terms of m epsilon 2kc, so the moment of order 2k, plus other terms which involve moments of lower order terms. Okay, and this is for the part where we have the reproduction. And for the mortality, we will use Taylor expansion on M to estimate this integral M and integral of MQ epsilon to be equal to M of M epsilon 1 plus some other terms, which will be of higher order. And we will also neglect some positive terms in this integral using that M is positive. And these properties allow us to write some equations on the moments, which are written this way. And here, F1, F2, and F2k are some terms which involve many terms. They're rather complex, but they have a nice property that they're of higher order terms in epsilon. So what does that mean? For the moment, of course, we don't know that what are the order of the moments, m epsilon kc. But let's suppose that we already know that they're of the right order. If epsilon, we know already that the moments are the right order, then we can see that F1, F2, and F2k are of higher order with respect to epsilon compared to the terms at the left of the equation. Okay? And also another observation is that in these equations we have a dissipative term. We have this plus 1 over half, 1 over 2 m epsilon 2c, with the positive sign for 1/2. And here also in the third equation, since we know that actually this is something that of course there's some work to do. We don't know already that m of m epsilon 1 is less than 1 in general. We know that initially it is, and we can manage to prove that it will remain less than 1. And for k large enough, then this term will become positive. So this term becomes a dissipative term. And then we use this classical inequality property that if we have this inequality on y, then we can control y by the infinity norm of f over k. Okay, so this is a simple, classical property. And using that, and from the equations that we had here, using a continuity argument, we will show the result. And how do we do that? It is that we assume that for some finite time, we know that these inequalities hold, but then we prove that if they hold for a finite time, they have to hold for at least some time afterwards. And in this way, we prove that they hold for all times. Okay, so in this way, we obtain these estimates on the moments, which are essential in the next step to obtain the estimates on the Wasserstein distance. Okay, now for this part, I will stop here and I will just comment a little bit the case of a steady state. And natural question is whether the approach can be adapted to study also the steady states. And also a natural question is, are all steady states concentrated necessarily? Okay, so I will try first to answer to this question. We can answer to this question in a particular case where we expect to have only one steady state, at least among the concentrated ones. Okay, and in this case, this corresponds to the case where 0 is indeed a global minimum point. So it's so the minimum of M is equal to 0, and it is greater than 0 anywhere else. And all the critical points of M are larger than 1. Okay, so we don't have any more candidate on concentrated steady states. And we also assume that M is strictly convex around 0. And in this case, we can prove indeed that the solution, the steady state, is necessarily concentrated. So let's M epsilon 1 and M epsilon kc be the moments of a steady solution, and sigma k be the kth order moment of a normal distribution with variance 1. Okay? So as I said before, what we expect is that the solution will be close to a Gaussian distribution with the variance epsilon squared. So we would have the moments of order k would be close to epsilon k to times sigma k. And this is something that we prove. We prove that M epsilon 1 is indeed bounded by some term of order epsilon squared. And so M epsilon 1 is in particular close to 0. So the solution is, the average of the solution is necessarily close to 0. And that all the moments of order k are close to the moments of a Gaussian distribution with variance epsilon squared. So here we have epsilon k sigma k. So M epsilon kc is close to epsilon k sigma k with an error of order epsilon k plus 2. So, and then the question is, when we have other extremum points with values lower than 1 plus m of 0, what happens? So in this case, we expect to have multiple concentrated steady states. This is something that was already proved in the paper by Calvez, Garnier, and Patou. And we can also adapt our method to obtain this. And also, in some particular situations, we expect to have some non-concentrated steady states as well in this case. And this is something that we are currently working on. So let me also mention some words on the existence and stability of steady states, and can we use our method to study this? As I said before, there are other approaches to study similar questions. So in order to mention the main ingredients of our approach, it is more convenient to switch to the equivalent formulation in terms of an epsilon, where the segregational variance is set to 1 and the death rate is m of epsilon times something, m epsilon x. In this case, the infinitesimal operator, we write it as a bilinear functional, T1 tilde, and we will use some fundamental identities. The first one is that gamma 2 is indeed fixed point of this operator. And another very interesting property is that if we put the derivatives of gamma 2 in this operator, there is still a nice structure, and the operator T1 tilde, when it is applied to derivative of order k and derivative of order L, we will obtain the derivative of order k plus L of gamma 2. And thanks to this structure, we can use Hermite polynomials to study our problem. So Hermite polynomials are defined by this relation, the derivative of order k of gamma 2 over gamma 2. And this yields an orthonormal basis of weighted L2 space with the weight gamma 2. And so what we can say is that T1 T1 tilde can be factorized in terms of these Hermite polynomials, and that we can also estimate the contribution of death rate, and it is usually, I mean, at least for higher order terms, this is small. And these two properties allows us to show the existence and local stability of steady states and epsilon, where an epsilon over gamma 2 is in the weighted L2 space. And thanks to this method, we can also control the distance of all moments of the steady states from the moments of the normal distribution gamma 2. Okay, so I will stop here and thank you for your attention.
Oh, thank you very much, Sepideh, for the very nice talk. Are there any questions in the room? Yes, Pascal. Pascal Maillard has a question. I don't know if you can see him, but he's on the corner of the room.
Hi, Sepideh. Thank you very much for the nice talk. Can you please detail a little bit more what possible difficulties you have in the moment approach, and in particular with the nonlinearity of the equation? So why do the moment calculations work out nicely? Can you give a bit more details on the calculations?
So you mean in the calculations here?
Yes, that's right.
Yes. They actually, this is I think that so the main ingredients are the ones that I have written here, that we can actually do things naturally, but we have to do them carefully and use some tricks to write the equations finally in this form. And once we have this form, using a continuity argument, we can actually close them. I'm not sure if so the trick is to write, I mean, to do, of course, some computations which have to be done carefully in order to write the moments in the equations in the moment in a dissipative way and with terms which are small, and then do the computations. But the idea is rather simple, actually.
Oh, okay, I mean, so if you start far away from a steady state, so how is it expressed in the moments, or is the moment calculation? Do you have to assume already that you're close to steady state, or?
No. What I assume initially here is that we are close to a Gaussian distribution. This is what we assume. I mean, indeed, for the moments, to have the estimates on the moments, we only need these assumptions, okay? That initially we are concentrated the variance is of order epsilon 2, and moment of order k0 is of order epsilon 2 k0, and that the solution is concentrated around the point, but this point can be very far from the point where we have the local minimum point, okay? But it has to be somehow in the attraction zone around it, because otherwise it will converge to some other local minimum, okay? So so this is the main assumption. But then what we prove is that the solution will remain close to a Gaussian distribution that is this one. That it will have a Gaussian shape, but this Gaussian shape, it will change its mean, and the mean will follow the gradient of m. It will go to the minimum gradually.
Okay, interesting. Thanks.
Thank you.
We have another question at the back of the room.
Hi, Sepideh. This is Emmanuel Charta, and yeah, I have a question regarding the previous slide, the one you just showed to Pascal. Yes.
Sure.
So about the initial condition, so you start with something which I think is compactly supported because of your assumption and the moments. So if you had started with something which is, let's say, of a width of order like greater than epsilon, could you kind of like explain what happens?
Okay, so this is something that I haven't done yet I mean, this is an interesting question that I'm interested in understanding it. For the moment, I can understand it only for the steady states.
Okay.
So, you know, in this result, we don't assume initially anything on the moment, but what we obtain is that for sure the steady state will become concentrated. And so this is rather new and it is not yet well written. So I would say that the dynamic case would be a next step. But for the moment, I expect that the solution will become concentrated first and then it will move.
Okay.
But for the moment, I haven't proved it. But we have proved it only for the steady state.
And a second question, if I may, like regarding like the slide right after, like the one before. Sorry. So when you describe the initial condition, yeah, right. Yeah, the one right after that. Yes.
This one?
No. Okay. So
No.
12. Yeah, right. So.
Just I don't know what.
12. Yeah, 12. I think. Yeah.
12.
Sorry.
Yes. 12.
Yeah.
Okay.
Yes.
This
right.
one? Okay.
So as you said, like you have the mean of the population evolving, I mean, following like the fitness gradient. But if I understand like your ansatz correctly, like the variance of the population does not vary with time. It remains steady. And I mean, I don't know much about those infinitesimal model, but I was under the impression that you had, I mean, it is believed that normally when you adapt, you have like a change of variance as time goes along because of like, I don't know, like Fisher, like fundamental theorem of natural selection, right? You see what I'm talking about?
Actually, there are many works in quantitative genetics where they assume, I mean, of course, there are different works and it depends on which one we are talking about. But I also know, for instance, the ones that I had mentioned here, they all assume that the variance is constant.
The variance,
and
yeah, right, yeah,
yes.
like in Landy, yes, that makes sense.
Yes,
okay.
they have many works where they, I mean, if you have
right.
if you have an asexual reproduction operator, then this could not be true at all. And this is why we have Hamilton-Jacobi equations that appear. So in the case of asexual reproduction, the variance changes a lot. But in this framework, at least under these assumptions, the variance does not change. And it is also in accordance with many works in quantitative genetics.
Yeah, right. No, you're right. Sorry. Yes.
Are there any other questions? So I do have two questions, and then maybe we can, if you stay online, we can keep discussing, and if other people are interested, we can still discuss further during. Oh no, because there is no. Sorry, I'm chairman. It's too early, but maybe you can we can discuss further during coffee break. So my first question is about uniqueness, because at the end you prove stability, existence and stability. Do you know anything about uniqueness of this?
Okay, so of course there's no uniqueness if we have several candidates for the steady states, for the concentrated steady states. But in this case, where I show where we show that the solution, the steady solution, has to be concentrated, I expect to have uniqueness in this case, and we are still working on it because we have to somehow combine this result with the next one on the fact that because we have a uniqueness result, a local uniqueness result in terms of the coefficients of Hermite polynomials. And it is the domain of this uniqueness result is very close to what we have here. But is it exactly the same? This is something that we are working on right now. And I hope that we will be able to show it, but we have somehow to make these coefficients uniform with respect to k. So this is the difficulty.
Okay, thank you. And my last question is like an open question about the similarities between this argument, which I found very spectacular with the Hermite polynomials. And I don't know, like kinetic equation, like maybe Boltzmann, because the Gaussian also plays a role. Is there some connection between what you did and over results?
Yeah, actually, after we understood that we can use Hermite polynomials, then we discovered that Hermite polynomials are used a lot in kinetic theory, and so it is they are used, for instance, in indeed for Boltzmann operator, but also for Vlasov-Poisson and other equations. So we still have to work to understand the links between these approaches and ours. But yes, the Hermite polynomials are used a lot.
Okay, fantastic.
And for instance, they are used a lot for for numerical studies, and for so I think that to write a numerical scheme and probably asymptotic preserving scheme, they should be able. It should be possible to use such results, and to do that, we have to understand well what is done in kinetic theory, because there are several articles in this direction.
Thank you. It's great. Thank you very much. So we can thank Sepideh again, and
thank you.
If we can maybe if we can postpone the discussion to the coffee break, Sepideh, if you have some time, we'll get in touch by email.